get to it. We have more questions here than we probably have time for. So we have an hour that they're giving us for this. So we'll try to hit as much as possible.
They now know that.
Wow, it's just like light traveling from the sun. 8 minutes until you know the Earth's being destroyed. So if there is an issue or there's something very specific that you want covered and we're getting close to like maybe like the half-hour mark or something, start throwing out requests for questions, and we'll see if we've got something that maybe hits more of what you want. Also, we have no idea how to do this. Oh, and as I promised everybody, here's the opening shot of the adjusting the camera. All right. Well, it's 10 o'clock. So
somebody retracted a message.
Oh, a message retracted already.
We may see a lot
and
of that.
Remember that we can also see your names when you're posting stuff. So let's keep that in mind. We know you are. Okay. So it's 10 o'clock. So let's start this review session. What do you think?
Well, I mean, let's just start with the very first one. I guess everybody's got this on the Google Doc.
Yeah, so there's a Google Doc that's associated with this that hopefully is being populated as we speak. This first question is get asked a lot, how can you do questions that have plotting or plots on a final exam? This one is a really simple question. You're holding a ball, you throw it straight up in the air, right? Comes down and you catch it in the exact same spot. Which of the following plots for position, velocity, and acceleration are correct? Now, the twist in the question like this that makes it a little bit more, I guess, trickier is that they're taking the down to be the positive direction. So we've already given you perhaps not an ideal set of what's positive, what's negative. So we got a selection of different ones. I guess let's switch over to the thing here. Now, one of the things that I wanted to try to get across to you is that sometimes when you do these questions, multiple choice questions especially, there's an easy way to literally just knock out ones right away. If you look at these, you know that acceleration is 9.8 meters per second squared down, consistent on the entire face of the Earth. If down is positive, that means you have just a constant positive acceleration value. So immediately, just by understanding that, you can look at these plots and you can knock out A and B right away. It immediately gets rid of them. Now, as Dr. Massa uses his adept art skills here to whip through this.
There we go.
There we go.
I got me a graph.
Right. So we can knock out those first two right away. Now that leaves us with position versus position or velocity plots for the last two to try to narrow down what you've got. C, the second one in C, shows an acceleration taking place or a deceleration occurring, which is not what actually takes place.
You're talking about the velocity time graph.
Velocity versus
so this
time.
is, let's see. Oh God,
I know this is horrible. Perhaps we should switch back and just literally show the picture up to the screen.
Hold it up. Hang on a second. All right, I think we'll get a lot of feedback.
Yeah, this will be great feedback. Yeah.
All right. So,
a question like that, which shows a deceleration occurring, isn't what's taking place. You have a constant acceleration down during this whole thing. The correct answer, of course, for this one is D, what you would expect to see for something like that. And I don't know. I think that's probably an easy question, but it's a way that you can kind of show plots being used for a final exam.
Right. Okay.
And a quick way to sort of eliminate versions that you wouldn't necessarily use.
Okay. So all right, let's sort of just recap in case anybody's
let's switch to the screen thing so we can actually hold this up instead of using the terrible our terrible use of.
There we go.
Yeah. Okay. No. So then.
All right. So
there.
Okay. Okay. So with multiple choice, with graphing, I guess the important takeaway in this question is, again, that down is the positive direction. Yeah. So we can play process of elimination, and we can get rid of, starting with the acceleration. We know that gravity is in a downward acceleration. So anything that has a positive gravity or a positive acceleration, positive is in the down direction, those will be correct. And so then you got rid of which choices based on that?
Positive, first two. So A and B are gone because they're both negative accelerations.
All right. And now we said when something goes up versus down, the velocity is going to change directions. It's heading in one direction, then later opposite. So looking at, was it A and C?
No, C and D.
C and D.
There's only one that occurs that way where you see the change in velocity.
Right. Right.
Or at least at the very point that, with a scenario like that, you throw something up and it stops. So at some point on one of those plots, there's got to be a zero velocity.
Right.
There's only one that shows that. All right. Well, we've wasted quite a bit of time on that first one that was supposed to be the initial one to go through. Maybe we should take a look at what the comments are and see how people are enjoying themselves during this. 10 a.m. Man, there's a 10 in the morning now too. It's crazy. Now let's take a look here. There's a doc you can access with the questions. Yes, there is. If you go to the news section on the 1080 site, there is a Google Doc that's associated with this right now. So that should be posted already in the news on the 1080 site. Or is it Course Link? What's called? Which one of these guys most likely to end up in prison? But depends what country, I suppose. Question 2. 2 is a good one. Do you want to do this one?
Sure.
The 2 is block of mass M is released from rest at the top of an incline of length L. It makes an angle of E with respect to the horizontal at the bottom of the ramp. The block travels horizontally before striking a second block. Mass is half the mass. After the collision, 2 blocks are stuck together. If all surfaces are frictionless, how fast are the 2 blocks traveling after collision? Express your answer in terms of G, L, and theta. A lot of people have issues with just doing expressions entirely in variables. So rather than having numbers, it seems to throw people. There's literally no difference in how you actually solve the question. You just skip the step of plugging things into the actual calculator.
Sure.
So probably for a question like this, the first thing you should do is draw a picture of what's happening.
Yeah, absolutely. And
we'll see how long that takes with the system.
All right, let me open this up again. So, all right, why don't you try drawing since I clearly cannot.
All right, so
here, let me delete this for you. All right, so again, this is the second question, should be up. I guess one of the things that you want to start thinking about right away is, all right, what kind of question is this? And if you can at least say what quiz maybe this came from, then that helps narrow things down. So it's a block of mass M. This is quiz 1 material. This is the first quiz.
Look at how much faster this is going when I do it.
Yeah, let's just ride that one out. Let's say that. Okay, so it's quiz 1 material. Yeah. We have a formula sheet that has everything divided by quiz sections. Whether or not you know specifically what formula this is, it buys you a little bit of time to start thinking about things. Now, we've got something going down an inclined plane. We know that it's going to speed up as it goes, so we can look at kinematics. We could talk about forces. And
this is also one I think that I tried to stress a couple times in class that you might get questions that combine separate sections. This can be done with energy and momentum combined as a style of question to solve.
Right.
And it's an easy way that in one question out of 25, where it's hard to hit the entire scope of everything in this course, you can combine 2 things. So keep an eye out for stuff like that too.
Okay. So the energy part comes in basically looking at this mass that started at the top. It ends up at the bottom. There's no mention of friction in here, so we're going to use energy conservation. It undergoes some loss in gravitational potential energy, mgh. There we go. And that h, we can use some trig to relate that to the length of the ramp. So that would be sine theta times L would give us that height. So that's the initial potential energy. And as it makes its way down to the ramp, that's going to completely convert it into kinetic energy. And what's nice about this is, as you said, this is conservation of energy and then momentum. What we're going to get out of this after rearranging a bunch of algebra is we're going to get V, what that speed is when it reaches the bottom of the ramp. Now, we're ignoring friction, air resistance, all this kind of stuff. Even if it hits the kink at the bottom and continues on, whatever that velocity is, it's going to redirect and travel horizontally with that speed. So we're trying to write a question here that's not overcomplicating with a lot of extraneous details. We get a final velocity just based on energy conservation. It's square root 2gl sine theta.
Yep.
Okay, so hopefully that makes sense to you guys.
Now, when it hits the bottom of that ramp, that velocity doesn't change because there's no friction, nothing involved. So as it's moving and strikes that second object, it's still traveling at that same speed.
Okay.
This is when the momentum part, I guess, comes into play.
Right, yeah, so we've got 2 objects now. Do you want to change the color?
I don't know. Let's see. Okay, so I go to color.
Okay, so we've got the big mass, capital M. It made it down to the bottom. It's going to slide along. There's no friction, so it's going to hit that small mass with the same V that we just calculated. So we've got one object moving initially, one object initially at rest. We've got momentum before the collision, and then afterwards they're going to stick together, so we'll have a momentum afterwards. So conservation momentum, we look at what's before, what's after. We've got M times V. This is not easy to write on. All right, we've got M times V initially. That's the B, the before, where it was just the one mass. The smaller mass had no momentum. And then afterwards, they hit and stick together. So we can express the final momentum as just the two masses total up times whatever that V final is. You want to put a little A or something there just to indicate that it's the after, if you can get over there.
Hey, there we go.
There we go.
So one of the great things, mass doesn't play a part in it. The masses cancel out in this one as well. If you look on the right-hand side of the equation, you've got mass plus a half m. So that gives us 3/2 m.
Okay, so the little mass was half the big mass.
Yeah, half
all right,
the big
that's
mass.
why it's capital. All
All right. So then you end up with root of 2g L sine theta is equal
not at all what you said.
to 3/2 m times velocity. Sorry if there's an m there. These m's cancel. And that just gives us 2/3,
okay,
right? Times the root of 2g L sine theta, and that's our new velocity.
That's the V final. So the correct answer would be C on this multiple choice question.
Now, the options that exist on that multiple choice are common mistakes. So I put in there if you didn't cross multiply correctly. So if you had instead of 2/3, you have 3/2.
Okay, that's choice B.
That's choice B. So that's a potential get wrong. If you didn't take into account sine theta. So initially in the height, if you just put L, that answer's in there too.
Okay.
Also, even if you just took the m to be a half and didn't combine the mass plus a half m afterwards, that's also an issue in there as well. So all of your possible options for answers are possible wrong answers. Okay. So that's just something to keep in mind. Just keep your steps together, go through them as pedantically as you can, and make sure you match stuff line to line.
Right. Yeah, I think that's the best advice. When you do a question on this exam tonight, the moment you work through something, if you see an answer, don't necessarily assume that just because you got something that matches that it's going to be correct. I mean, this question I'd say is one of the more challenging, more involved kind of questions you might see on the exam. But again, it's designed to test how well you understand what you do.
Yeah, 1 plus a half is 3/2. Yep. So we add the two masses afterwards. So so there's an issue where the 3/2 come from. People are asking.
Okay.
The 3/2 comes from as that mass comes down. You have two masses. The big mass is capital M. The small mass is 1/2 m. You're looking at mass before times velocity before is mass after times velocity after. They both strike and move together in that question. That's conservation of momentum.
I don't know. Should we give a few minutes if there are any other?
Yeah, let's let them catch up. This 15-second delay and this terrible ability to draw on this tablet is really affecting these things.
Yeah. So, all right. If anybody has any questions, even if you want to ask expansion or, I mean, what variation?
This is a good question. This question too. I would say that this is probably computationally, I would put this at like sort of the higher end of what you would expect on an exam. Again, not a lot of tricks in it, but this is going to take you the full 5-6 minutes to do a question like this.
Sure.
Let's take a look there. Nothing's coming up in this 15 seconds window. Let's see. Okay. Tension question. Where did the sign come from? Where did the sign come from? They give you a length L that it travels down the actual incline of the ramp. The height, MGH, and the stream is going to be posted afterwards. This height is actually L sine theta. So remember, you're using your right angle triangle thing. That is L sine theta.
Let me see it. I'm just going to try to highlight the right angle triangle.
Right. So theta is given to you as that angle that the incline makes right there.
We got a right angle
triangle here. And that makes sine of theta the opposite component, the y component.
Over hypotenuse.
If you were to take cos, it would be the one that's on the same plane that the horizontal plane.
Maybe the fact that your H is actually.
I apologize.
Maybe
let's just make that look more like an H. That's way better.
Okay.
All right. Let's look at. Do you want to skip to 4? Question 4 is the torque question.
Yeah, we can take a look at that. Oh, we just had a flurry.
We have a flurry of questions here.
Okay.
How much the exam is on heat? There is, as I mentioned in class, there'll be anywhere between 1 to 3 questions on heat.
Why was the first velocity you solved for was the velocity? Okay, all right. Here, why was what we found here?
The velocity before.
Yeah, this is the before the momentum collision. What we found was to get to the bottom of the ramp, you convert potential energy into kinetic energy, and we took energy conservation up here, and we found what that V was. So that's the V at the bottom of the ramp, but we call it V before because it's V before the collision here. So here's our momentum.
Remember, everything with energy and with momentum, you can split into sections, right? So they're always before or after something occurs.
This is awesome. There. That's a cool one.
Yeah.
All right. Okay, let me just quickly check, see if there's anything else, and then we can maybe take a look at something.
I say we do torque and then we do some bubbles.
Okay.
Yeah, okay.
All right.
All right, good. Like I said, this will all be posted after the fact. And based on how terrible these our drawing on this tablet is going, maybe I'll also write up an actual solution to the ones we can cover,
Sure.
just so that you can actually see them properly written out.
Yeah.
Let's take a look at question 4 is a torque question. I know a lot of people have issues on torque. I guarantee you there's at least one torque question on the final, if not more than that, or other questions that involve torque, like rotational motion, some of torques, right?
Yeah. Did you do a review with these guys? Because
I did not know.
I think one thing that I always tell people is, I mean, torque is notoriously, it's the hard one, torque and scaling, right? So there will be a question on there. There always is a question on torque. There's always a question on scaling. But remember, this is a comprehensive exam. There's 25 questions. So to put 5 torque questions doesn't make any sense. That's not.
You figure there's 12 weeks. You get 2 classes a week. So there's about a question per class.
Right. So
with a couple extra on heat.
So expect 1, at most 2, like if there's a momentum combination question or something like the continuity equation, which came up in every fluid dynamics question, you can see multiple occurrences. But here you can expect it. But remember, if it's the kind of thing that this is your kryptonite and you spend 10 minutes on one question or 15 minutes on one torque question, it's only one question of the 25, and you might be better off leaving it till later or something like that and not wasting 15 minutes on one.
I would recommend reading the entire exam first, starring the ones that you know how to do, and do those first. Yeah. Because if you can get them and you have them done right away and they only take maybe 2 minutes a piece to do, they'll give you a ton of time at the end to tackle ones that are hard questions. Yeah. Also, sometimes when you look at one and you can do it and you've been working through it, ones that you don't know how to do, click in your brain a little bit later in the exam. Oh, wait, I use this part of the way I set up question 5 is actually how you do question 2.
Right.
Well, we only had a limited time. Do you want to do torque and then move into like bubbles or something?
Yeah, let's do torque. So this is the question 4 on the, or whatever. Let me jump back here and we can try.
Question 4, it's got 3 different forces listed on a grid. It's got a pivot point P, and the question is, assume the magnitude of each force be the same. Rank the torques in order from lowest to highest about P. This is almost exactly a question that I gave on last year's exam. I feel it's a good way to sort of quiz you on the 2 methods of doing torque while not having to go through a whole bunch of complex computations. So basically, this one just says you've got all forces that are the same. That means that the only thing that varies is your actual R distance or your moment arm to them. To do this one quickly and easily, you need both methods of torque to be able to do it. So Dr. Massa is attempting to draw this grid here.
Painstakingly.
So this first one, F3 is the easy one to look at. That's the one that's initially on the left there that Dr. Massa is drawing.
You talk about this and I'll draw some.
Okay, that's a distance of 1 unit away. So right now that gives us a value of 1 times the magnitude of the force. So that gives us a value of what that torque for 3 would be there. Right now he's drawing F2. Right. Now if he's drawing F2, we notice that this one here, oh, he's making a straight line. Nice. We notice here that, again, that force is the same value of force, but it's a weird distance away if you were to try to take that perpendicular distance. And then you'd also have to do a bunch of the geometry to try to get to it to go from there to there. Yeah. So that's a tough one to do. And you don't, if you only know the one method of doing torque, you can do that with the grid that's laid out there, but you don't need to do it that way. You can use that second method of torque. For the second method of torque, you just extend that F2 on both directions away along that moment arm. You make that line of action that we talked about in class. So you make that distance there. All you need is the perpendicular distance to that distance, which again is just 1 grid unit. And so that perpendicular distance that Dr. Massa is drawing right there is 1. You have a value of R1 and a value of F2. That's the same as F3. So right now, F2 and F3 create torques that are equal.
All right. So this then is essentially, let me just overlay back that. These are the 2 forces, F2 and F3. It turns out that they generate exactly the same torque. In the first case, we've got the distance R of 1 grid space. In the second one, using the second method here, this crappy dashed line that I've drawn here is also one grid space. So they're both what, counterclockwise and the same magnitude of torque.
Yeah, and this one just says magnitude. So this one isn't even asking positive or negative direction. So as far as you're concerned, those two are equal. There's only one option of your 4 choices that has equal torque 3 equal to torque 2, and you can pick it right there without even doing the first one. If you want to do the first one, looking at F1, F1 is acting at an angle, but it is actually a perpendicular distance that you can resolve. It cuts right across the diagonal of that one grid point going there. So in the end, it's the square root of 1 squared plus 1 squared. So it's root of 2. Okay. Root of 2 is like 1.4. So it's actually the biggest value of torque that you get. But you don't even need to go that far. And that's something to keep in mind when you're doing these exams. If you see a question like that and you see the answer, and you feel like you've done it properly in your gut, you've got the correct answer right there.
Well, let me just grab that discussion board. How many, do you guys feel comfortable with the first two, F2 and F3? Is everybody comfortable recognizing that those are the same torque using the 2 different methods?
How are they equal? Perpendicular distances are the same. Yeah. And that's basically that. So fundamentally, this comes down to that argument of the first and second method of torque. Can you explain why they're equal? Yes. Yep. Yeah, okay, so people are getting it after this delay. Yeah, so those are those 2 methods. And if you can do those 2 methods, you've got it right there. So why are they equal? We'll do it one quick last time, go right over again. So 2 methods of doing torque. The F3 is doing the first method. The first method is you look at the perpendicular distance to where the force starts, and then you take the perpendicular part of the force that acts in that direction. It is acting at exactly 90 degrees in both cases. So you have the distance of R being 1 grid unit and F just being the same value of F for everything. Let's now look at F2. F2 is at a weird distance away that you can't necessarily figure out. But if you use the second method of torque, you draw a line of action that extends both to the left and to the right of what that force is. You see it there in red. And then you go from your point P down in a perpendicular distance to what that line of action is. That is also 1 grid point. So that means they are the same torque.
Okay, so let me just improve this dotted line here. All right, that's our perpendicular, which is perpendicular to the force. This is our F2.
Yep.
Okay.
All right. So I think that's a quick and dirty way to do torques. It's also a quick and easy question for somebody to put on there.
Yeah, I would say this is a reasonable exam question. I wouldn't call this the hardest you could have for torque.
I'd say it's a mid-level. I'd almost say this borders on what we would say when you say like concept questions, where you look at something like this and it's like conceptually you can look at that and you can use the different things we learned about torque, but there's not a ton of computation to be done.
Right. How many, let me get rid of this, see. So do you have an idea then, or a ballpark for these guys, how many concept questions versus straight up numerical versus graphing?
So this exam has been written by myself, Dr. Ball, and Miranda.
Okay.
In terms of concept questions, we get 25 questions. You're probably looking at maybe 4 or 5.
Okay. All right. So yeah, I think that's good. 20 to 40%. I mean, yeah, 40% is maybe a little much, but
it's one of those ones where, to do the questions themselves, to do all the math, you have to have some questions that are very quickly doable to be able to solve 25 questions on a 2-hour exam. Yeah. That's a long exam for stuff that's pretty computationally full like this.
You know what's awesome? These guys
finally to say.
Well, yeah, they can. Thank you very much, because this is like super unwieldy. So
I know, and it's great. You guys are actually helping each other, which is fantastic. This is what would be called teachable moments. Well, trick questions. There's no trick questions in it. The only thing that I was mentioning before is stuff to look for. So like in that first question where we said the direction down is positive, so you're given a thing that sometimes you might overlook when you're going to solve. Okay. Quick explanation for F1.
All right, let me pop back there.
Okay,
let's do that.
So we'll look at F1 again. If you're looking at F1, F1 is at a vertex. It cuts straight across to an opposite vertex there. So there's a perpendicular distance to that. It's the same way as if you were working on F3. And the distance from P to where F1 starts, you just use Pythagorean theorem. So what is that distance? Well, you've got in the X direction, you're moving 1. In the Y direction, you're moving up 1. So that hypotenuse, this red line there, that hypotenuse that Dr. Massa is waving over right now, is equal to the square root of 1 squared plus 1 squared, or the square root of 2.
Yeah. So, I mean, here, I think the important thing in this question, because this is more a conceptual one, is if people can recognize that this line R for the force F1, this is bigger than the R's that we used in calculating F2 and F3.
Yeah.
So those 3 R's that go in, we end up multiplying each of those by force F1, F2, and F3. And this one is the big one. It's diagonally across a grid space as opposed to along one of the side lengths. So you're not asked numerically what that is.
Mm-hmm.
It's 1.4 times whatever grid space is, but if you can recognize in this case that it is bigger, then you know that you can push that to being the largest of the 3 pillars.
All right, we're about 20 minutes in on this. What do you want to do, Mike? Do you want to do your the scaling one? People have issues with scaling.
Scaling, we can talk about that.
Well, we can throw it up. I mean, let's throw it to the people. We've got a scaling one. There's a bubble one. Maybe the pulsatile flow one. Who wants what? Do you want to see? Yeah, that's a hypotenuse for F1. Do you want we have a scaling one we could do right now? Scaling, pulsatile flow, or a bubble?
All right, somebody said scaling.
Scaling.
Okay, scaling.
Scaling.
Okay.
All right, scaling. Scaling and bubbles. Let's do that.
All right.
Now, the scaling one's also a heat one, so that's a nice combination. Some people have issues with heat right now. For heat, so this is a scaling one with heat. Recognize that heat, just like energy, just like momentum, are ones that you can combine into other questions. Okay. So this question is question 7.
Suppose you made 2 cups of coffee.
Yes, suppose you made 2 cups of coffee. Suppose you made 2 cups of coffee. One is an espresso, which is smaller, 25 grams. One's an Americano, which is 675 grams. It's a larger one. So you've got a small thing and a big thing, right? Both cups have the same shape. So that's an indicator that we're looking at the, look at that, 2 squares, that we're looking at scaling.
Yeah, isometric
scaling. And each coffee has an initial temperature of 90 degrees. They cool down to 80 degrees over a given time. Which of the following statements is correct?
Okay. So let me start by saying that when I wrote this question up, this is not necessarily, this would be very hard. This would probably be one of the hardest questions on an exam. And you might get a couple of this level at most.
It's funny. It is one of the hardest ones, but you can also do it in like 3 lines.
Right.
But
right.
So yeah.
It's hard because of scaling. And I sort of wrote this as just a way to revisit all the different scaling ideas.
And it also, you might look at a question like this and think Newton's law of cooling, right? You have something that's a certain temperature, it drops to another temperature. Good way to recognize that it's not that is you're not given the surrounding temperature.
Right.
So a Newton's law of cooling question, you need to be given the temperature that the thing is at, the temperature that drops to the temperature of the surroundings. So you have 3 different temperatures. That's not here. So you might look to, okay, what's a different style of solving this question?
Okay. So here, this is a scaling question, and we've got a small and a large cup of coffee. You're given the masses, and the things to keep in mind are that when we compare different quantities, one of the things we always do is relate it back to proportional to some length scale, where this could be the height of the mug or something like that. So mass, where's that?
There it is.
Yeah. All right. So when we talk about the mass of an object, mass is proportional to L cubed. So the way we start is with a ratio that we know. We're given the ratio of masses. And we'll do the big one over the small one.
So you got mass of the Americano over the mass of the espresso.
Right.
Which is equal to 675
over 25.
Over 25.
Okay. And so pull your calculator out, that ratio is equal to 27. So step 1 is work with the known ratio you've got. And step 2 would be to work it back to the ratio of L's. We sort of discussed tons of scaling quantities, always in proportion to L to some power. So we can say that ratio 27 is equal to the ratio of lengths cubed.
I guess that's equal, not just proportional.
Yeah. So what we need to do then is we can learn what the ratio of the lengths are. Here, let me just call it the height of the coffee cup by taking the cube root of both sides there. The cube root on the right-hand side will give us the ratio of L's. The cube root of 27 is 3. So we're looking at 2 cups of coffee that are same shape, but one's 3 times as tall, 3 times as wide, 3 times as thick. It's got 3 times the length of the handle, 3 times the diameter of the cup opening. Now, what we're asked in this is about which one's going to cool faster. And we can think of this in a couple different ways. In class, you talked about the amount of heat produced by your body, the amount of heat contained in an object. And so we can think of this as the more mass, the more heated coffee you've got, the
intensity
more,
is power per area, right? So it's, well, sorry. Go ahead. Yeah.
So we're looking at the amount of heat contained in it. They're both at 90 degrees Celsius. Did you guys talked about Q is equal to MC delta T, right? So here we're looking at the amount of heat involved. And because the Americano is 27 times as heavy, it's got 27 times as much heat. So this comes back to the idea that the heat generated or the heat contained by a body is proportional to its volume or its mass. So there, why don't actually toss down the can you write like the ratio of heats or something like that? Do a different color. Let's go back to fuchsia. A lot of people like fuchsia early on.
Okay, I'm in fuchsia.
All right, so the ratio of the amount of heat now is proportional to volume. I think that's an intuitive leap that you want to make.
Sure. So your heat is proportional to L cubed?
L cubed. All right, so 27 times is massive, 27 times the volume, 27 times the amount of heat. Now, when we look at heat loss, we talked about heat being expelled through the surface, through the system. It's just like cells when they expel whatever byproducts of their whatever biological system, it goes out through the surface. So heat loss is proportional to L squared. It's proportional to the surface area of the object. So when we consider the fact that the Americano has 3 times the height, width, length, L squared, a factor 3 squared, it's going to have 9 times the amount of surface area.
So if we want to look at then heat loss of the Americano for the heat loss of the espresso, that's equal to L squared over L squared.
Right.
LA over LE is 3. So that means that you have 3 squared, and that means you've got 9.
Okay.
So if you simplify that, that means that we can literally look at this and say the heat loss by the Americano is 9 times the heat loss by the espresso.
Right. Okay. So the Americano loses 9 times the amount of heat, but it's also got 27 times the amount of total heat. So when we think about cooling something down, we had when we talked about thermal energy and stuff, we had Q is equal to MC delta T. We know these are cooling down by 10 degrees from 90 down to 80. So we're looking at the total heat loss and how quickly that happens. We've got 27 times the amount of heat in the Americano, and it loses it at a rate of 9 times faster. But comparing these two, we're going to say that the ratio, the balance between, are you just checking the board?
Yeah.
Why?
Good.
Okay.
Christian last name, am I going to fail? I don't think so. You're putting in the time here. I think this is an easy thing to pass if you're putting in the work.
Okay. So here, let's get a little clarification here. So heat loss, the rate of heat loss, how quickly you lose something is based on your surface area. That's why you go outside in the winter, you wear a coat, you wrap your body in something to insulate that surface boundary between inside and outside. So the heat flow is proportional to surface area. And here we're talking about that as HL. So heat loss, the flow outwards.
A quick note on scaling. I think people often, you might have been trying to get a shorthand in the textbook. They sometimes tell you to memorize the 2 to the 2/3, or this is proportional to the 3/2. I never do it that way. I always break it down to, I find out what my thing is. I see if it's a mass, it's proportional to the ratios of the lengths to cubed. And then I work it down to what that ratio of the lengths are and scale it back up. So I never go to a 2/3 or to a 3/2. I find L over L, and then I go up or down from there.
So looking at the discussion board, this is not the final answer yet. This is a daunting question. And I prefaced it by saying that I put this question up here for discussion purposes. This is a hard question. It's one that you guys handled in class. If you looked at back to when, if you guys did the sort of the baby, how much it loses heat, the rate of heat production to heat loss. It's that kind of question. But what I wanted to focus on was just these relationships and making sure that we understand them. So let me backtrack and go through this here. We have the ratio of masses is proportional to L cubed. This is one that, again, this is not on the formula sheet, but I'm hoping that everybody's comfortable with that. The ratio of mass is proportional to L cubed.
Mass goes by volume.
Right.
So you're looking at L cubed.
Right. Surface area, another fundamental one, is proportional to L squared. We need to know that one. Now it's associating the heat loss. Now, heat loss comes out of your body, out through your skin. The heat loss is proportional to the amount of surface area you guys have. And so that's going to be proportional to L squared. Again, that's another thing that you want to memorize going in. Once you make that connection, the math is not that difficult. But it's being comfortable with writing things as ratios. So heat loss is proportional to L squared. And when we look at that, the Americano, which has 9 times the amount of surface area, will have 9 times the rate of heat loss. That's not the answer to this question, because we need to combine it with, well, you might lose heat a lot more, but if you've got a lot more heat available for loss, then it's counteracted. And so that's where up here on the top, we have H. Maybe let me change that to, maybe I'll write it as a Q, or maybe I'll just make a fat mess of everything. Hang on a second. Let me, and very, look at this eraser. There we go. The amount of heat in the big cup is more. It's got more heat in there. The amount of heat that a body of hot coffee has is proportional to how much mass there is, right? Again, come back to what you did in your heat section where we had Q, the heat is equal to C delta T. So the more mass you've got, the more heat you've got. For say Guelph Lake, which is at 4 degrees Celsius, that's a crap ton of water. It's got a ton of heat stored in it. So the Americano is bigger. It's got way more heat stored in it. They're both at 90 degrees Celsius. And because the amount of heat is proportional to L cubed up here, it has 27 times the amount of heat. So down below, it loses heat 9 times faster, but it's got 27 times the amount of mass, 27 times the amount of heat. So
this is an evil question.
It's totally an evil question, guys. It's totally an evil question. I did this. I like to discuss things, guys. That's why I put this here. So it's a hard question, and I don't think this is a reasonable to expect as a final exam question. But my point in talking about this was, do these general ratios make sense to you? The ones that I'm indicating with an arrow. That's the takeaway.
Well, look on the discussion board and see what your,
all right, let's
your
see
wicked
what
question hath wrought.
Crap storm okay. Okay. Yes, boss. Yeah, that's sweet. I'm a boss. Okay. All right. So that's good. The final answer then in this one, which again, this is a super tough question, would be we've got to consider if it's got 27 times as much heat, but it loses it 9 times as fast. The fact that it's got more heat, it'll take the Americano will take longer to cool down to 80 degrees Celsius. And I imagine intuitively you guys all know this, right? If you have a big fat drink of coffee, it's going to stay warmer longer than if you've got a little one. These are all sort of intuitive ideas that now it's becoming challenging because we're putting math to them. So let me go to the question. There was the list of choices here, A, B, C, D, and E. Now we know that the Americano will not cool faster. It's bigger. It's the big one. We know that we can trust our intuition on that. So the espresso will cool faster.
So, I mean, even at that point right there, even if you can't, if you're not able to work your way through all of this stuff properly, you at the very least know that the espresso cools faster.
Right.
So you can knock out the Americano ones.
Right. So let's get rid of B and D. Those are wrong. The Americano will not cool faster. So then we've got A, C, and E. And the espresso will cool faster. It's not going to be 27 times as fast. We saw that 27 is one of the numbers. We saw that 9 is one of the numbers. But because we're comparing those three, it's got way more heat. It cools 9 times more, but 27 times as much heat. It's the ratio of those two that gives us the answer. So the ratio 27 over 9, 3. It's got 27 times the amount of heat. It's losing it at 9 times the rate. The final answer is E, that it will lose heat. The espresso will lose heat 3 times as fast. That's the big takeaway. And again, that's something that should have been in your lecture notes back when you talked about scaling. An example like that with the baby versus the adult losing heat and why you put those cutesy little outfits on newborn babies, that kind of stuff. All right.
All right.
Okay. So I think I'm hoping that with nothing
now
else,
that you've destroyed their confidence,
yeah, let me. Can I explain why Q? All right, so look at the formula on the top right. Q is equal to mc delta T. Q is proportional to mass, and the mass is proportional to the volume, or the L cubed. So Q is equal to mc delta T. It's proportional to mass. It's proportional to L cubed. All right. Let me get out of this thing.
It's good. There was a comment there that hopes and dreams have been shattered. It's good for that to take place at least at some point, even prior to. All right, we're coming in 20 minutes
Okay.
left. All right, what do we want to look at? We've got a bubble question that is equally as destroying Dr. Mass's bubble question. We have pulsatile flow. We got osmolality, osmolarity. We've got diffusion. What do you want to call this? Diffusion terminal velocity question.
Oh, we've got I see bubble osmosis.
Osmolarity, osmolality, you can probably bang through this quick, right?
Yeah, let's do that.
That's a quick one. So we'll do that one quick, and then we'll spend the rest of the time on bubbles. Somebody's waving. Hello.
Okay. All right, let me clear this off. So the question on the osmolarity, osmolality.
So osmolarity, osmolality question is question number 9. You have an erythrocyte, which is isotonic in a 0.35 osmolar solution. You place it into a sodium chloride solution of molarity 0.2. The question is, the cell swells, shrinks, and by how much?
Okay. So let's start with the cell here. Now, we got to unpack these kinds of questions. There's always 2 stages of information in these things. There's the before and the after. So let's start with the before. The erythrocyte, the red blood cell, is isotonic in a 0.35 osmolar
So that's
solution.
0.35 inside here?
Yeah, so that's isotonic. Just means it's
gosh, it's already screwed up.
Isotonic means it's happy. That's what its normal status is, 0.35. And that's...
God. Keep going. I'll fix this. Don't worry.
This is 0.35. That's the nucleus right there. 0.35 osmolar. So put a little OS there. All right. That's what its initial concentration is. And we're going to throw that into a sodium chloride solution.
And the sodium chloride is 0.2 molarity. Right?
Okay. So the surroundings is 0.2 molar. It's sodium chloride. And the key to remembering with this, the whole osmolar versus molar thing is that when we're looking at the flow of water, water cares about how many ions or how many individual entities are in the surrounding concentration. So 0.2 molar sodium chloride, when you throw that into solution, it dissociates into sodium ions and chloride ions. So we're going to have 0.2 moles of sodium, 0.2 moles of chloride. And water doesn't care about the difference between them. It just sees a total of 0.4 moles.
And that's osmolar.
So that's osmolar. That's the osmotically active concentration that's going to dictate the flow of water. That's what osmolar means. So we've got inside, we've got a concentration of 0.35. Outside, we've got a concentration of 0.4. The way that these osmolarity questions work is we focus on what's going on in the cell. It's in this massive bath, and the cell is going to shrink or swell in response, but nothing is going to change the outside environment. So that 0.4 surroundings is fixed. Let's focus on what's going on in the cell. We often throw up this equation here. V initial times C initial is equal to C final times V final. And that's the concentration and the volume. And that's simply because when you multiply C times V, that's just the number of moles of stuff that's in the cell. And that stays.
Yeah, that's a universal number for this scenario.
Right. So that's why it's constant. We're looking at the junk inside the cell being constant. Now, it's got some initial volume VI that we don't know about. It's got some initial concentration, 0.35. So we'll just leave VI as VI. We've got a final concentration. It's going to match the surroundings. So it's going to take on a final concentration that is the same as its surroundings. And we're going to look at how the cell changes in response to make that happen. So it started at 0.35. It's going up to 0.4. It's getting more concentrated. And since we can't get the junk out of the cell, what we have to do is blast the water out of the cell in order to take the existing matter inside and make it a higher concentration. So we should expect to see that V final should be smaller than V initial. It shrinks to make its own internal concentration greater. So we end up with this one formula. you have to lay out the before and the after, and the math is really straightforward once you've identified the molar versus osmolar stuff.
And now if you take a look at the actual selection of the question, the answers to the question are, you have swells by 14%, shrinks by 13%, swells by 75%, shrinks by 43%, swells until it bursts. If you look at the initial, the final volume is 87.5% the volume initially. That means the whole thing shrinks by about 13%.
Okay. I love this. These guys are like coaching each other here.
Nice. Well, then, so this becomes the thing. All these questions about osmolarity all break down into changing concentration from molar back to osmolar.
Right.
And again, the most questions you're going to get about something like this on the final is going to be likely like one question.
Oh, yeah. Yeah. So it seems like from the discussion board, a lot of people got this one. In a situation where the cell is in a solution of glycerol and has no glycerol inside it, would it swell and burst? If so, why? Okay, before we tackle that's like the most challenging of these questions. How are you guys just with the way this question was laid out? I think this is what we've given you.
It's a by the books osmolarity.
This is a typical exam level question. Again, there's always going to be one or two questions that are harder. If you were given a glycerol question, we could talk about that. That would make this.
Here's a quick one. What would the number look like if it was swelling? If the number looked like when it was swelling, you would have a 0.4 over 0.35, say. You have a number bigger than 1 on that side of the equation if it's swelling.
Okay, so yeah, let me change.
So I think they're good. Somebody said they're good with that.
Okay,
yeah.
All right.
So let's talk about the glycerol one for them.
Okay, so the trouble with glycerol is, unlike sodium chloride, it is able to go into the cell. All right, the sodium chloride makes the water flow because it cannot go across the cell membranes, but glycerol can go. And so what we have to do when we have glycerol involved is we have to look at the flow of glycerol and the flow of water. Both of those things can happen. And my suggestion is you look at them one at a time and sort of see whether you're going to lead to something stable. So let me just sort of grab this. I'm going to try to move this to the side or something in case we need it.
Just pick it up, move it.
Yeah, and I'll sort of.
No, yeah, just oh, there you go. Look at that. There, it's moving.
All right, let me put this aside. Let's say that we've got 0.35 osmolar inside the cell. Can you like make it here? Let's make it blue or something.
Yeah.
All right. So suppose you had. I don't know if I sort of work through something like this. Let's see. Why don't you put, say, 0.2 molar or 0.2 osmolar of glycerol on the outside.
God, here we go. Okay. So 0.2 molar?
You know what? Make it, we could just make it, yeah, all right. Make it 0.2. Okay. All right. Yeah. So 0.2 molar glycerol. Okay. So both water and glycerol are going to flow. Let's think about what the glycerol is going to do. Glycerol, it diffuses. It diffuses from a high concentration to a low concentration. So looking at the inside of the cell, there's no glycerol in there. With individual molecules, they diffuse based on their own concentrations here. So glycerol is going to want to enter the cell because there's nothing on the inside, but there's 0.2 on the outside. That's Fick's law of diffusion. That's another topic for the final quiz. So the first thing that's going to happen is we're going to assume glycerol flows in. It's going to flow in, and the final concentration of glycerol in the cell is going to be 0.2. Okay. Okay. All right. Now, glycerol, the concentrations are much smaller. Flowing glycerol in is not going to swell the cell up itself. It's the water that does the changing of the cell size, right? We're looking at 0.2%, which means we're looking at 98, 99% is water. So when water flows in and out, it has a massive effect. 0.2 glycerol flows in. Don't write that. Yeah. All right. So let's look at this now. We've made it so that the glycerol is happy. It's got 0.2 on the inside, 0.2 on the outside. Now let's look at what's going on in the cell, and then we'll start thinking about water. So it's got 0.35 osmolars of its own junk, mitochondria, ribosomes, all that kind of stuff. And now it's got an additional 0.2 of glycerol. So the total concentration of stuff inside the cell has gone up to 0.55. Now, from water's perspective, water has inside the cells 0.55. Outside it sees glycerol, 0.2 osmolar. So what's going to happen? We've got a high concentration of stuff on the inside. We want to make it balance to what the surroundings looks like. So we need to dilute the cell down to 0.2. And to dilute that, we need water to flow in. So water is going to flow in and it's going to intend to reduce the concentration from 0.55 down to 0.2. That's an H2O as opposed to H sub L question mark. Yeah. Okay, so water is going to want to flow in. Now, these things don't happen. They don't take turns to happen. But let's think about this. Water is going to flow in and say it's going to dilute the insides of the cell down to 0.2, meaning it's really going to swell the cell up a lot. It's got to cut the concentration by more than half. So the cell is already more than doubled. That's probably enough to indicate that the cell is going to explode. But I mean, remember, when we throw water in, we're diluting everything down, which means the glycerol inside the cell that used to be at 0.2 is also now being diluted. So, and it's being cut by a factor of at least 2, right? So now we've got glycerol is being reduced inside. The concentration goes down. Glycerol is also going to start to flow in because it wants to maintain its own internal concentration and external 0.2. So by water flowing in, glycerol dilutes. Glycerol is going to flow in, which is going to ramp up the concentration of junk in the cell. Water is going to flow in to dilute that. And we've got this amplified effect where they're never going to reach a happy equilibrium. The cell's just going to take on more and more water until it lyses.
The answer is kerplowy.
Yeah. So that, again, that's a challenging question for the cell stuff. I hope that makes sense. Let's just open up this. The glycerol. Okay. Did that make sense to you guys? Why all glycerol goes inside? Glycerol is permeable, or glycerol can make it through the membrane, so it will. It's the sodium and chloride ions that can't, and that's what forces water to flow instead. We got people talking about two different things.
Okay, we got 10 minutes left. So is there something specifically that people want to cover? We've got still...
No idea what lice means. Guys, one thing, let me say, if there's any language on the exam that you don't know, like lice and erythrocyte and these kinds of things.
Yeah, feel free to ask.
Ask. There's no harm in asking. There's going to be a ton of invigilators in there tonight. The instructors are all going to be there. Don't not ask a question for clarification. We're not testing your vocab, we're testing your physics understanding. So please don't not ask a question.
There's a million bubble requests coming in. So we're going bubbles to out, hopefully.
Okay.
Question number 6, an air bubble, radius 0.1 millimeters, sits within a pressurized water tank with depth H equals 51 centimeters. Thick layer of oil, density 0.8 times 10 to the 3 kilogram per meter cubed, distance of 70 centimeters deep, floats on top of the water surface. The opening of the tank is equipped with a mercury-filled manometer with a reading of Y equals 10 centimeters shown. What is the gauge pressure inside the bubble? So this one's triply complex.
This one's super hard.
Yep. So you have this idea that you've got a pressurized tank. You've got 3 levels basically in it, right? You've got a water bubble below the surface of water. Above that, you've got a surface of oil. And then there's a manometer attached to the outer the top of the whole thing to give you a reading of another pressure differential, basically, right? The extra bit that you are looking at that has a height Y associated with it. So you've got these 3 levels of pressure over top of the bubble itself. Now, for a bubble question like this, you are looking at bubbles underwater. That means it is only one layer of surface. That means there's only one value of the surface tension to look at. So our quantity for that is going to be the 2 gamma over R, right? And not the actual doubling of that.
Can we look at this in stages? Why don't?
Sure, yeah. Let's do that.
Oh, hang on a second. Let's take this one step at a time. This is, again, guys, this is much more involved than an exam question. This was, foolishly, I put together thinking, we should discuss this. And then...
so draw the bubble there somewhere.
Okay.
In the water level there.
All right. Here's our bubble. Let's just deal with...
So for now, let's just deal with what the pressure would be for the water.
Okay. The water's blue, though.
Yes. Yes, it is.
All right.
All right. So you've got, if you go to your formula sheet, you've got your expression that delta P is 2 gamma over R. That is for a bubble of one surface, which is what we're looking at here, where you have water.
Okay.
Surrounding an air bubble.
So when we compare the pressure inside the bubble to the surroundings, inside versus outside, the pressure inside the bubble is going to be greater by an amount 2 gamma over R.
Correct.
So we've got, oh my
geez.
God.
You want me to do this? All right. Yeah. So we've got here that delta P right now is equal to 2 gamma over R.
And that's comparing inside to outside.
Inside to outside. Now, you've also got a level of water above that. So there is a rho GH on top of that, right?
Yeah.
That rho GH is the density of water. G times the height of the water, which in this question is what?
51 centimeters.
So 0.51.
Okay. So again, that's the height from where the bubble is to the surface of the liquid. There's our H. That's a nice H. Okay. What we're calculating here is the pressure differences because of the bubble surface and because of the depth of the water. What we're looking at is a gauge pressure. It's measuring the difference in pressure from one point in space to another. And if this in itself is a typical exam question where we'd be asking, what's the pressure in the bubble, the gauge pressure relative to, above the water surface? That's what gauge means. And so we'd plug in our numbers. The surface tension of water is given to you on your formula sheet, 0.0728. We've got the radius of the bubble is, 0.1 millimeter. So here, just make sure that you convert to SI units. 0.1 millimeter is 1/10 of a millimeter.
Yeah, so 0.0001 meters.
Right, so 10 to the minus 4 meters. And then we've got density of water, which is on your formula sheet, G. Everybody knows what G is. And Orbex is written here, 0.51 meters, 51 centimeters. So it is a game of units, and you could very well get a question that is just this, where really the different choices are, did you remember to convert from centimeters to meters or millimeters? And we'd throw in some red herrings for if you forgot those conversions.
All right, so we're coming down in 4 minutes.
Okay.
All right, so the next level that you add on top of that is a level of oil, right? So you're looking at this green layer that's 70 centimeters deep. All that does is it increases the pressure that you feel, right? So you add in a level on top of this. So if you're looking at green, we got this green layer here, it adds this other value, and you've got and you've got another added height in there.
Right.
This added height adds a level to this pressure. The added pressure is just literally the weight of that level, right? So it's the density of the oil times G times, in this case,
it was 70 centimeters, 0.7 meters.
And that is also a gauge pressure.
So we've just been basically isolating all the different reasons to cause an increase in pressure in the bubble compared to the air above the fluid.
So now this question also adds another layer because Dr. Mass is a jerk, and it puts in a manometer. This manometer now is full of mercury. There is another level here, right? And so you look at this and you say, okay, this is lower here, it's higher here. That means there's more pressure inside of here.
Right.
It adds a pressure to it. Lower, there's less stuff pushing on it. Oh, can you roll that back up, I guess?
Nope.
Lower, there's less stuff pushing on it than higher. There we go. Oh God, everything's going crazy here. So this is lower, this is higher. That means there's a bigger push here than there is here. That means there's an added pressure. So we add one more. To add to this, you've got the density of mercury now times G times the difference in that height, which is 10 centimeters.
Okay.
And that all together is the total gauge pressure of the system.
Okay.
What's the absolute pressure? Throw an atmosphere on top of that.
Right. So
take a look at the board here to see what the actual questions are.
Okay, yeah.
Since we're running out of time.
All right, don't worry about the mercury. Here, let's do this. In the interest of time, let's not worry so much about this. This is something that I threw in for discussion purposes. This is already, the way that we've listed this question is a fairly substantial exam level question. So don't worry about that. Maybe what I'll do is afterwards we can post what the correct answer would be, just considering.
For each level.
Yeah, for each level.
Now, I guess one of the questions would be, when do you not add into this? you know, if everything's always adding another layer, are there times when you take away a layer? What is the 2 gamma over R? That is the surface tension. That's the pressure of a bubble.
I think it's clear that we're reaching the end of the hour here. Now we're just,
yeah. So
okay.
In terms of looking at the pressure, you're looking at added pressure levels going on top of that. People have issues between what's gauge and what's absolute pressure. Gauge pressure is literally a comparison between 2 points. You're just taking P at one point, subtracting P from another point. That's the gauge, as if you were literally taking a tire gauge and putting it across 2 values.
Sadio just wants his name mentioned, or her name mentioned. Sadio, jeez.
I don't see anyone.
He said PP. Well,
mean square displacement. We got a mean square displacement question coming in. We usually use root 6 dt. We have 3D movement. Could give us some examples that wouldn't be 3D. So looking at diffusion. Diffusion that happens in 3D is anything happening in real space. Gel electrophoresis is an example of 2D, where you've got diffusion taking place over just a plane. Sure. Looking at diffusion through an actual artery or an arteriole is 1D. So there are examples where you have constricted motion taking place where it's not 3D.
I think the context, if we're talking about random motion and you got drunk and blindfolded yourself and ran around on Johnson Green, you're moving in 2 dimensions, forward, backward, left, and right. That would be an example of 2D random motion, assuming you were suitably primed for that and blindfolded. That's a good science experiment.
All right. Well, I guess that concludes this theoretical review. We'll put up, I guess, better written solutions to some of these then.
Yeah. Or just trying to think. There's questions. When do we subtract the pressure?
Yeah.
So the only case where you'd subtract the pressure is if you see something like the gauge that I crossed out. If the level was higher versus lower. Anytime you see one of those manometers where the liquid level on the inside is one's low and one's high.
So they can actually see you doing comparisons.
Here, let me draw.
Yeah, that's good.
Anytime you see liquid level that's unbalanced, say here in this manometer, we've got low level and high level, and there's liquid higher on the right.
If you look on the left-hand side is a higher pressure than on the right-hand side because more stuff is pushing down, right? Pressure is force per area. That means there's more force on the left-hand side than the right-hand side. That means it's a higher pressure, so you have to add that quantity. If you're looking at the inverse of that, so say you were coming from the right-hand side instead, that is a higher level of the manometer versus a lower level of the manometer. That means that there's not as much pushing down. That means it's a lower pressure. So if you're trying to find what the pressure is over there, you would subtract that difference.
Right. Okay.
That's probably about all we can address with these last ditch questions that are coming through. So in the end, as a quick sort of review, I guess you've got 25 questions for sure. You got 2 hours to do it. That gives you about 4 to 6 minutes a question to do, right? Don't get hung up on the first 5 questions and take an hour to do those. I've seen that happen before where literally you walk through and somebody has finally gotten the 4th question. They spent a whole hour and they've still got 25 or 21 more to go after that point. So go through, I say, read it, see what you know how to do, see what you don't know how to do, save what you don't know how to do till the end.
There will always be a handful of questions, say 5 questions or so that are straightforward, no jokes, no tricks. I mean, it's just like plugging in a number and going with it. So look for the questions that you're most comfortable with and start. So much of these exams, the stress and anxiety it's all momentum. And if you can fire through in say 15 minutes, you fire through 5 questions, that gives you enough confidence to realize that the rest of it's possible. So look for not necessarily doing the first question right away, but look for a few that you know that you can handle, and that'll see you through. That'll get you going.
Yeah, don't get hung up on time. Make sure you check your units, keep your positive and negatives, make sure your calculator's set properly, look at the difference between degrees and radians, centimeters and meters, kilometers, seconds, minutes. Check for things like that.
Yeah.
And I guess that's it.
Yeah, you guys will be all right. You'll do fine. Don't forget to not ask questions if it's a language thing, if it's anything like that. Worst case, he's going to tell you he can't answer the question, and that's useful, right? I mean, that's yeah. What day is the exam?
All right.
Yeah, all right.
Good enough.
All
See
right,
you guys tonight.
Thanks a lot.